The final video for section 21.2 is going to work through several examples on graphing piecewise function. This is to give you a significant amount of practice so you can feel comfortable with the topic. Now let's take a look at this next example. In this case, we've got a function that's defined for every point except a single point, x equals -3, and then that point is filled in with this given information right here. So we can start off with the easy point, which is this one right here, and just say, okay, we need to plot the point -3 and 27. So we go to here to -3, we go up to 27, and we put a solid dot there. Now let's look at the more complicated piece. We've got this rational function, x cubed plus 27 over x plus 3. And again, this isn't defined for -3 because if you plug in -3, you end up with 0 over 0. If you want to pause the video here and verify that, please do. So let's pick a few other points that we can use on this graph. Let's start with, say, -4. We'll put in -3 and we'll talk about how we can find the limit so we can find an approximate there. -2, -1, 0, and 1. So if we plug in -4, we end up with when we plug in -4, we end up with 37. Again, you can't plug in -3, but you can take the limit. So if we look at the limit as x approaches -3 of x cubed plus 27 over x plus 3, then we know we're going to have to factor this because it's not defined. So if we factor x cubed plus 27, we end up with x plus 3 and x squared minus 3x plus 9 over x plus 3. And that nicely simplifies those x plus 3's. And once we do that, we plug in -3, and we end up with -3 squared, which is 9, -3 times -3, which is 9, and 9. So 9 plus 9 plus 9 is 27. Hey, that worked out very nice, didn't it? So our limit here ends up being -27. So we've got that open dot where our closed dot is. When we plug in -2, we end up with 19. When we plug in -1, we get 13. When you plug in 0, you get 9. And finally, when you plug in 1, you get 7. So let's plot some of these points. At the -4, we're at 37, so -4, we go up to 37. At -3, we have an open dot at -27, so it's going to go around this red dot. And again, that's because it's the limit. It's an open dot. It doesn't actually equal anything there because we have this inequality, but it is going to approach that infinitely close on both sides. -2, 19, so almost here at 20. -1, 13. 0, 9, just under 10. And then 1, 7. So the thing that we have to be careful of here, we've got this curve, obviously, that's filling in by connecting those dots. But we don't know exactly what happens here. Does it go back up? Does it go down? So we want to pick a few more points to fill in. Let's pick 2, 3, and 4, just so we get a clear picture of the graph. If we plug in 2, we end up with 7 again. We plug in 3, we get 9, so now it's starting to go back up. And if you plug in 4, you get 13. So you can see here it's symmetric here. So we're going to have a vertex here in between 1 and 2 at 1.5. And we end up with a parabola. So let's plot those points. 2, 7, it's going to stay there. It will dip a little bit below that. 3, we go back up to 9. And 4, we go up to 13. So again, we end up with a parabola. So again, we look at the function. We want to determine the domain and range. The domain in this case, again, if you look at the x values, it's given. we can include all the real numbers. And again, the abbreviation for real numbers is just that capital R with that extra line there. It's kind of like making it bold. Or if you want to use set notation, again, you can say negative infinity to infinity. The range, on the other hand, we can see here that we have a low point. It's going to be at 1.5, and that's going to be our lowest y point here at x equals 1.5. And then we want everything greater than that. So we want to make sure we plug 1.5 into our function. And when we do that, we end up, as we suspected, a little bit lower. If you plug 1.5 in, you end up with 6.75. So our range is going to be all y such that y is greater than or equal to 6.75. Or we're going to have a bracket here because it's greater than or equal to. We're going to start at 6.75 and go up to infinity. And again, we close that off with parentheses. So again, what we have going on here, we've got our graph here. We have this weird point right here that fills in the graph. And then we have the domain, we can plug any numbers in. The range, we only get an output of numbers greater than 6.75. The last question we have here is asking if it is continuous. And again, continuous means that you could draw this graph without lifting up your pencil. The blue line, we cannot do that because we have a hole. But luckily, and this is the nice thing about piecewise functions, we can fill in that hole with that little red dot. And that's why we call it a removable discontinuity, because we can remove the fact that it is discontinuous by plugging in that hole, or we can remove one single point. So yes, it is continuous everywhere because the point -3, 27 fills that hole that we had there. So take a second, look all of this over, make sure it makes sense, and then we're going to move on to the next example. So this next example, you notice here that we're missing a point. We have x is less than 2 and we have x is greater than 2, but we don't have either of those equal to 2. So we are missing a point here in our domain. Again, if we want to look at the first part of our function, we have 1 over x minus 2. Now you should notice here that 2 does cause an issue, because if we plug in 2, we end up with 0 in the denominator, giving us an asymptote. So let's just draw that in to start off with. So again, this is x is less than 2, so let's pick some points that are less than 2. Let's pick, for instance, -2, -1, 0, and 1 to start off with. So if you look at plugging in -2, you get 1 over -4, so -1/4. If you plug -1 in, you end up with -1/3. If you plug 0 in, you get -1/2. And if you plug 1 in, you get -1. So if we were to plot these points, we've got -2 is really close here to the axis. We have -1/3, which is not much further away from the axis, at -1/2 at the point 0, -1/2. And at 1, we are at -1. Let's plot a few more points just to kind of see what's going on here. Let's plot the points -3, and let's pick the point 1.5. So we plug in -3, we end up with -1/5. And if you plug in 1.5, you end up with -2. So -3, -1/5, so that's even closer to the axis. And 1/2, we get the -2, so at 1.5, we are going to be here. So you can see how you're going to have this asymptote, and we know we should have this asymptote because this is a proper rational function. And then if we just kind of connect those dots, we're actually going to see that this goes down to -infinity. These numbers are getting negative. They're all negative, and they're getting bigger and bigger in magnitude. So we've got this asymptote. We knew we had an asymptote. It's going down to negative infinity. The other function here is quite simple. 2x plus 1 is just a linear function. We can plot points if we want to, especially since we can't actually use the y-intercept because the y-intercept is not in the graph because we're starting at x equals 2. Again, the y-intercept would have to be when x equals 0. So in this case, we'll pick the point 2 just so we know where we're starting with. Again, that's going to create an open dot, and we'll just pick a few more points. So if you plug 2 into 2x plus 1, you end up with 5. You plug 3 in, you get 7. And you plug 4 into 2x plus 1 here, you end up with 9. So if we plot those points at 2, we are at 5. And again, we've got an open dot because it's only greater than, not greater than or equal to. At 3, we are up at 7, and that's a closed dot. And at 4, we are up at 9. So we've just got a straight line there that's going off to infinity. And so this is our graph. It's not real pretty. It's definitely not continuous because you've got an asymptote and an open dot that kind of goes off there. So we can answer that question right away. No, it is not continuous everywhere. The domain in this case, again, we left out that point x equals 2, so we can either write it simply as x such that x does not equal 2, or we can again use that set notation going from negative infinity to 2, union with 2 going to infinity. And that's taking each one of these sets. So x is less than 2 gives us the negative infinity to 2, and the x greater than 2 gives us the 2 to infinity. The range, on the other hand, if you look here, this one again is a little bit more involved. We've got this blue, which looks at all of the negative numbers. Again, we've got an asymptote, so we're never going to quite reach 0. We've got it going off to negative infinity. So the range would be the y values. It'll be a little bit easier to put it in set notation. So we've got this lower set, which goes from negative infinity to 0. And again, that's parentheses because we've got a horizontal asymptote on the x-axis. And then we're going to union that with this set up here. That's the red set. And the red set here, again, we've got a parentheses because we have an open dot, and it is starting at 5. And then it's going off to positive infinity. So we're missing all of the y values between 0 and 5. So again, if you need a second to look this over, please pause the video and do so now. I do want you guys to pause the video at this point and try one of these yourself. When you're done, resume the video, see how you did. Again, always make sure that you don't overlap the graphs, that you have that barrier line between where each one starts. So pause the video now, try it out, and then resume the video and see if yours matches. For this example, you should have picked a few points for the top curve, the x cubed plus 1. I picked -3, -2, -1, and 0. Again, you always want to pick that endpoint, in this case 0. And I got the following y values. Now, based on the units on the graph, we couldn't graph this -3, -26, but you can see how it does kind of work because it's going to drop drastically after this point that we plotted here at -2, -7. The second part of the graph, the second piece of the graph, is a very easy function. It's just a constant function of 1. The thing we had to be careful of here is that we had our open dot. Again, it's only x is greater than 0, so we have an open dot. We can't have redundancy here, or else it doesn't pass the vertical line test. So we have to have an open dot there, and then it just is a straight line off to the right. So if we look at the domain in this case, we've got everything covered, all of the x values, so x is a real number. Or if we want to write it as -infinity to infinity, that's fine. The next thing we want to look at is the range. In this case, our y values, again, range, we're looking at y values, how high or low this thing goes. And you can see here it's capped off at 1. It never goes higher than 1, but it does go down to -infinity. So y in this case, we can either write it y such that y is less than or equal to 1. It does equal 1, this whole line here. Or again, we can write it as negative infinity going up to 1, and again we use that bracket because we're including 1. Question again, is this continuous everywhere? Well, yes it is. Thankfully these points here overlapped. You can see here at 0 you have 1, and that's where it's starting here with the red function. So yes, this function is continuous. So we'll get a few more examples just to make sure you guys have enough practice with this. The next function is x squared plus 1 from this interval of negative 1 to 2, and then the linear function negative x plus 4, which happens when x is greater than or equal to 2. You could also write this a little bit easier as x is greater than or equal to 2 if you prefer. Either one of these are the same thing. So again, let's look at our top function here. We're going from negative 1 to 2, so those are the values that we're going to pick for our x. We've got negative 1, 0, 1, and 2. So when you plug in negative 1, you should get 2. You get negative 1 squared plus 1. You plug in 0, you get 1. You plug in 1, you get 2. And you plug in 2, and you get 5. So let's graph that real quick. We've got the points. I'll zoom in here a little bit so we can see the axis. You've got the point negative 1, so about here. And then we're going to go up to 2. At 0, we are at 1. At 1, we are at 2 again. And we have to make an open dot here. This is open because it's only less than. At 2, we are at 5. And again, we have that open dot. And so all we have here is this part of a parabola. We can't draw an arrow off because we're only starting at negative 1. This is our ending point on the left and our open dot ending point on the right. Now let's look at our second piece of the piecewise function. Again, we're picking any numbers greater than 2 in this case, and it's greater than or equal to 2. So we'll pick 2, 3, and 4. So you plug in 2, you end up with 2 because you get negative 2 plus 4. You plug in 3, you get 1, and you plug in 4, and you get 0. Again, this is going to be a closed dot because it's greater than or equal to 2. So at 2, we are at 2. So closed dot here at the point 2, 2. At 3, we are at 1. And at 4, we are at 0. And in this case, we can draw the arrow off because it's greater than or equal to its all points, whereas this one was confined to just a specific range. Again, we don't want to make this line go up here because that's not included in the graph. This line only starts at 2. We can only draw this part of it. Same thing for the parabola. We can only draw this part of it. We don't draw arrows in either direction for this one because we're included on a small interval, not the whole real numbers. Again, if we look at domain in this case, we start here at negative 1, but then we get everything after that. Again, looking this way, you can see how all the points are filled in after negative 1. So again, we can either write it as x such that x is greater than or equal to negative 1, or we can write it as negative 1, again with a bracket because we're greater than or equal to, going up to infinity, and again, close parentheses. Range, we have to be very careful here. In this case, we will end up with all the negative values here. We got everything on this red line is going to be from 2 and lower. And then the blue function stops up here at 5 and covers everything between 2 and 5. So our range in this case is y such that y is less than 5. It's not equal to 5, but it is less than 5. And again, if we wanted to write that in set notation, we would be going from negative infinity to 5, and we would be using a parentheses because it's not included. It's pretty obvious here to see that this is not continuous because there's a big jump here, and this is what we call a jump discontinuity. So no, there is a jump at x equals 2. Again, we always need to make sure that We only include the values for which we are given. So we have one more example here. Again, I want you to pause the video and try this last example, and then resume to see if yours matches the graph displayed. So for this example, you should have gotten this three-way piecewise function. You've got this truncated line, this blue line here. It starts at the point -2, 1, and then it goes up to an open dot at 1, 4. Again, because we are not including 1 at the point x equals 1, we graph the dot 5. And then we again have an open dot because we've got x is greater than 1. And we've got this straight line, this green line here. So if we look at the domain here, we are including everything, x values. You got up to here, it's an open dot, but it's filled up here, and then another open dot and continuing down. So our domain in this case is, again, x such that x is greater than or equal to -2. Or if we want to write it in the other notation, we've got bracket -2 to infinity. And again, we've got a bracket because it's a closed dot or greater than or equal to. Range in this case is a bit trickier. We've got this point up here for 5. We've got this range here where we've got our y values going from 1 to 4. And then we've got this green here, so that again starts at 1 and goes down to infinity because this arrow here can continue on because we're greater than 1. So in this case, y is kind of funny in that it is y is equal to 5 and y is less than 4, but not equal to. So it's going to be all of these, and again, this one picks up here and continues the rest of them. This one's a little bit easier to see in the set notation, possibly. Again, we're going to be starting with -infinity, going up to 4. We'll close that off and union it with just the point 5 to 5. So it's just a single point there. Continuous everywhere, definitely not. You can see all of these jumps here, so it is definitely not. It is not continuous everywhere. So this concludes the video for 21.2. Please go online and complete your homework now for this section.